Okay, so in class we already talked about how to identify characteristics of a rational by looking at a graph, but sometimes the graphs aren't always reliable to look at and you need to know the characteristics beforehand. So the first thing is a vertical asymptote, which we know is an invisible line that the function will never cross or equal. And in a little while I'll show you how this invisible line corresponds to the zeros in the denominator. But looking at the graph right now, we can see that the vertical asymptote will take place right here at x equals -4. That would be my vertical asymptote because the ends of the graphs will approach that -4, but they will never cross this or equal it. So vertical asymptote, x equals -4. The horizontal asymptote, we mentioned before that it's also an invisible line, but it corresponds to the degrees of the numerator and denominator. We'll talk about that in a moment. But lately we've been saying that a horizontal asymptote is where the end behaviors approach. So the ends of the graphs, we want to know what are the ends of the graphs approaching, what y value, what output are they getting closer and closer and closer to. So if you follow the end of this graph, it looks pretty much like it's hugging the y value of 1. And the same thing over here, this end of the graph is also hugging the y value of 1. Therefore, we're going to say our horizontal asymptote is at y equals 1. Okay, and the last thing that we're going to cover today is the removable discontinuity, which we can also call a hole in the graph, which is a coordinate that got removed from the function. And most of the time the calculator will not show you where this hole is. You have to be able to find it algebraically on your own. I'm going to go ahead and tell you where this hole takes place on the graph, and on the back side we'll prove how to find it by hand. So this hole is going to take place at the x value of 3 and a y value of 5/7. Okay, so we're going to go up to the graph and we're going to look for the x value of 3, which is 1, 2, 3. And right there, right below the 1 of your y value, which, you know, 5/7 is the same as like 0.714 something. So if you put it in your calculator, it'd be about right here. It's not yet passing the 1 because we know that these values are just going to approach 1. That hole would take place on the graph right there. That would be 3/5/7, which is a coordinate that got removed. Okay, so before I show you how to find everything algebraically on the back side by just using the equation of a rational function, I want to go over the basics. What is the #1 rule of fractions? Okay, so if I give you 2 examples, and this is a common misunderstanding that kids always do, if we have 12 divided by 0, everybody makes it sound like, oh, 12 divided by 0 is always going to be 0. And I'm like, okay. And then I say, well, what about 0 divided by 12? Then they say it's 0 again. They can't both be true. These are 2 completely different fractions. So when I ask you to prove this, then you're going to prove it. Well, does 12 go into 0 0 times? What I mean is, if I put 0 here and I divide by 12, 12 times what would give you 0? Well, that's 0. That's why this is still a true statement over here. If you have a 0 in the numerator, you know that the fraction will just equal 0. But over here, we can't say that it's 0. Because if I put 12 inside and 0 outside, 0 times what number will give me 12? And then everybody looks at me puzzled. It is impossible for you to multiply 0 by a number to get 12 because we know the rule that anything times 0 is supposed to be 0. So this is what we call something that is actually undefined. And what your calculator is going to tell you if you put this in there is it's going to say error because it's not a defined value. 12 divided by 0. Error, divide by 0, because we know that it is not possible. This is the #1 rule to remember. And we're going to use this rule to help us figure out all the characteristics that we've been talking about, well, except for the HA. Okay, so on the back side, let's get started. First of all, if I'm asking myself, what makes this equation undefined, it's really hard for me to look at the denominator and figure out what x could I plug in that would make this 0. I can't figure that out. That's why always when I give you something in standard form, go ahead and factor it right away. And on these, we can use the a equals 1 rule since both of these values have a 1 in front. So using my a equals 1 with the numerator, go ahead and do expanding. A times c is -6. The b value is -1. What factors of -6 will add to give me -1? And that would be 2 and 3, but the 3 would have to be negative. 2 minus 3 is -1. Using that a equals 1 shortcut, we know that we're going to have 1x in each factor to give me back the x squared. And we know that we're going to have +2 and -3 from the expanding portion that we just did. Okay, let's do the same thing with the denominator. Go ahead and expand. That way we can write the factors down here. Okay, so a times c is -12. The b value is 1. What factors of -12 will give you 1? Well, that would be 3 and 4, but the 3 would have to be negative because 4 minus 3 is +1. Therefore, we get x minus 3 and x plus 4. Well, looking at this fraction a little closer, we have a common factor that gets divided out. It gets removed from the function in a sense. Because x minus 3 divided by x minus 3 is 1, we can cross these off and just be left with x plus 2 over x plus 4. Now, before I did this piece, I want you to stare at this for a moment. Before we even simplified it, if I were to ask you what would make this fraction undefined, what x value can I plug in to this fraction that would make this equation undefined? And remember what I mean by undefined. I mean, well, if you divide by 0, it's not possible to get an output. You're going to get error because it's undefined. Therefore, I'm asking what x value would make the denominator 0. This equation would be undefined then for an x value of +3. Why? Because if I put a 3 here, 3 minus 3 is 0. It doesn't even matter what's in the numerator. I could put the exact same numerator here. I could put 0 here. It doesn't even matter what this factor was. Because we know that 0 times this is going to make a denominator of 0. And we know that that is going to cause this fraction to be undefined, having a 0 denominator. The same exact thing happens if we have an x value of -4. Because if I plug -4 right here for this x in this factor, -4 plus 4 is also 0. All it does is reverse this, but again, we would have 0 here, where 0 times that is still going to give you a denominator of 0, which either of these cases causes a undefined fraction. Okay, so now what does this mean? What does this undefined value mean? Well, what factor was actually removed? Keyword was removed from the denominator numerator. Well, we removed the x minus 3. Okay, so since I removed the x minus 3, and we know the fact that even before I simplified it, it was originally part of the fraction. So it's still some sort of discontinuity, something that causes the function to be undefined. It makes it discontinuous. Well, if it's being removed, we're not going to call this an asymptote. Instead, it's like a hiccup in the graph, and it's going to be a removable discontinuity. That's why I said the key word was removed. Okay, so how do I find this removable discontinuity? Well, kind of we already did it. We said that this takes place, it's discontinuous if the x value was what? What causes this to be undefined? Well, if x minus 3 is 0, right? If this whole portion is 0, like I just showed you, right there, if this is 0, then the whole denominator is going to be 0. So what x value did we figure out earlier that caused it to be undefined? Well, if you solve this for x, you're going to get x equals +3. But hold on, Mistress Mala, because a removable discontinuity is a whole. It's a point. It can't just be an equation. Well, on the front side, I even gave you a point. I told you it was 3, 5/7. Well, what part of this coordinate did we find? We found the x value. What's still missing? The y value. So how do I find it? Well, we're going to substitute the x value that we just got into the remaining factors, which would be these right here, whatever's left over once you simplified. And why would we plug that in? Well, because this all is equivalent to your y value. You plug in an x, you get a y. Why can we not plug it here instead of the simplified version? Well, if we plug it there, we're going to get undefined. So we can't have that. We want to know what the y value is that comes with that 3. So my y equals x plus 2 over x plus 4. And using the x value that we know causes this to be undefined, we're going to find the y value that is also undefined with it. So plugging in our x value here, we get 3 plus 2 over 3 plus 4, which gives us a y value of 5 over 7. Bam, we've got it. Therefore, let's write our coordinate officially. We have our x value of 3, and we have a y value of 5 over 7. You found the whole. Okay, so the next portion is even easier. What other factor was in the denominator, but it did not get removed? So if you look back up here, okay, well, we look in our denominator, we removed the x minus 3. We already took care of that discontinuity. We said that that represented a hole in the graph. But there was still some other factor that caused this equation to be undefined. And that took place with that x plus 4 factor. And we said, okay, well, what else was there? The x plus 4 was still there. And it wasn't removed. Well, we're not going to call it a removable discontinuity. What characteristic do we define on graphs as an x value that is something that causes the graph to never cross it, never touch it, it cannot exist? Well, you should be thinking of a vertical asymptote. Because out of vertical asymptote, that x value causes none of the outputs to be defined. So none of them will be crossing that x value. Well, this occurred if x plus 4 was 0, right? Because that would give us a 0 denominator if x plus 4 was 0. And what x value did we say caused this to be 0? Well, that x value would be -4. So x equals -4 is your vertical asymptote. And if we flip it over, that's exactly where that took place. X equals -4. And this was the hole that we defined, the RD, 3, 5 over 7. So far we took care of 2 of the things. The last piece is a horizontal asymptote. So a horizontal asymptote is something that the end behaviors approach. It does not mean that it is undefined necessarily. It's just something that the ends are getting closer and closer and closer to, but they won't equal it on the ends. Sometimes you can still equal a horizontal asymptote in the middle if it crosses it, which we've talked about. But the main thing we need to know is, what does a degree mean? Well, a degree is the highest exponent of a variable, not of a number, of a variable in a polynomial. So what does this mean? Well, if I give you a random polynomial, let's say I give you x cubed plus 2x minus 3, a random thing. I just made this up. Well, you look at the variables, I see a variable here, I see a variable here. A degree of this polynomial would be the highest exponent, which is 3. So the degree would be 3. Okay, well, what if we didn't have an a variable? So for instance, what if I just gave you the polynomial 3x plus 2, or I gave you just 3? Those are 2 separate things. Well, here I have a variable, so I have a degree, but the exponent of this variable is just 1, then the degree would be 1. If I have nothing but just a number and no variable, well, we know that the degree corresponds to the variable exponent, not a number. So we wouldn't say the degree of this would be 1. We would actually say the degree would be 0 because we do not have a variable. So now that we know what a degree is, I'm going to teach you 3 different rules. And if you look in your calculator, basically what these mean is how the ends work. So the first rule is same degree, which you can read it, but I'm going to summarize. Same degree means you'll have something like x squared over x squared, because the degrees would be the same. The exponents would be the same, the highest exponent. And it doesn't matter what number is in front. We call these numbers our coefficients. If you have a same degree, the rule is to say that your outputs will approach the quotient of your coefficients. So same degree means divide the coefficients. So my HA would occur at y equals 2 over 3. Similarly, if I had x squared over 3, x squared, then my HA would occur at y equals, well, the coefficient here would be 1. It would occur at 1 over 3, and so on. Well, if we look at our example, we have same degree. We're not going to look at the factored form because factored form breaks up those exponents. We want to look at the original standard form. The exponent here was the squared. That was the highest. This was also the highest. So we're using same degree rule. And both of these coefficients is a 1. Well, 1 divided by 1 is 1. So what's my horizontal asymptote? It is 1 because we use the same degree rule. When you get to pre-calculus, pre-calculus will explain the way that these work with limits, because the ending behaviors is talking about a limit. What do they approach? But for right now, we're just going to teach you the 3 rules. So same means divide coefficients. Okay, the next rule I like to call is top heavy. And if it's top heavy, well, obviously the bigger number is going to be at the top. So what would that look like? Well, the degree would have to be the biggest number at the top. So I'm going to put x cubed up here, and I'm going to put an x squared down here. If it is top heavy, that means that you're going to have the highest degree at the top compared to the bottom. And if you think about this, the biggest number will always be in the top then, because if it's being cubed, it's going to overpower the number in the denominator. So basically, this number will get infinitely bigger and bigger and bigger, regardless of what x you plug in. So as it gets bigger and bigger and bigger, you're not approaching a single value. So if you have this top-heavy scenario, you're going to simply say no horizontal asymptote. You will not have one exact value that you are approaching, because it will grow infinitely. The numerator will get bigger and bigger and bigger. So top-heavy, no horizontal asymptote. Okay, and the last rule, and then we're done. The last rule is bottom heavy, the opposite of what we just discussed. And bottom heavy is the opposite, so we're going to switch this around and put x squared over x cubed, because now the bigger number would be in the denominator. But what happens if you keep dividing by a really small number? For instance, dead calculator, I get 100 squared divided by 100 cubed. Well, that's really close to 0. But let me make this even bigger. 200 squared, divided by 200 cubed. That's even closer to 0. So the bigger that these numbers get, the closer and closer and closer and closer to 0 you will get. So the ending behaviors, if you have a bottom heavy scenario, is going to approach 0. So my horizontal asymptote would be at y equals 0. All right, so now that we went through all of these, it's time for you guys to practice it. If you need help, come to tutoring, please. Goodbye.